Let's see. I guess we're up to 26. So I've been here. I heard from Finn that some people are having some difficulty with part of the homework. That there seems to be a number of people asking kind of the same question. I think I could maybe help sort that out first. So does anyone want to try to articulate a question about what the derivation data type looks like for B expression? Can you hear me? Can anyone hear me? I don't know. I was having trouble with my speaker. Uh-oh.
Yeah, we can hear you.
Okay. So does anyone want to, so what you had to do in the homework is I used this one down below here to build this big step evaluator. And then we built down here also a let's see, what is this doing here? Here's the data type for derivations for A expressions. And so like with that ANUM rule, there's no premises, but for plus, I have like, let's say A1 plus A2 evaluates to, want it to evaluate to an end, and you split. I have the, actually I have the small step rules here, but so they're, I'm sorry, yeah, these are the small step rules, which are different, but the rule would look like this, except that you'd also have an A2 evaluates, and instead of evaluating to an A2 prime, it would be to a V. So I guess I could write it like in here. I could say like something that looks like, some A expression plus, and so this is actually though, like the keyword plus, and another A expression, and I'm just going to draw an arrow to mean big step evaluates to V. And so here's the rule, right, is that A1 better evaluate to V1, and A2 better evaluate to V2. And there's kind of a side condition that says that V is equal to V1 plus V2. Whoops. So the proof rule for that, like the derivation for that, is going to be, suppose that, so evidence for A1, let's say that D1 is a derivation that A1 goes to V1. And suppose that D2 is a derivation that A2 goes to V2. Then what is the proof rule for A plus R look like? It looks like, and you can build these by using the proof function to look at them, but I mean, doing one by hand maybe helps. The proof looks like A plus R, meaning it's the rule for arithmetic plus. The A expression that you have is this one. And then the derivation that justifies this is you plug in the derivation D1 and you plug in the derivation D2. So that would be a derivation that would give you, where you'd use this rule. So if I oh, come on. Sorry about jumping all over the place here, but all right, I want to get sorted out. Okay, so now if I start GHCI and I load bims.hs, so now I could try like the proof, and I want to say plus, let's say time, it's mult, and to, whoops, is it n or num? Num. Okay, and so I displayed the proofs, tried to display the proofs in a way that kind of gives you the structure, but it doesn't show you the terms. So if I go up here, so I don't know, maybe I shouldn't call this show. Anyway, it should probably logically, it should be down below. Sorry about that. It should be down below where is the declaration? Did I just kill that too? I must have. Okay, maybe it was in the right spot. Undo. So if I turn this off, and then I go and add to the this data type, deriving show. Now I reload BIMS. And now I reprove this and I get this. So this is trying to show kind of a tree structure, and it's basically saying, okay, look, I'm trying to prove that N2 times N3 plus N7 evaluates to 13. And the rule that I apply to try to show this is a plus R, and the double bars here mean, okay, there's two there's two premises to the rule. And the first one is to show that N7 evaluates to 7, and that's by the num rule. And then the other one is this bigger thing over here that says now you got to show that N2 times N3 evaluates to 6 using the Moltar rule. And that has two derivations above it. And one of them is that the left case is that N2 evaluates to 2, and the right case is that N3 evaluates to 3. So this is kind of a pretty print that shows the structure of the proof. But maybe this one shows it better because this is the raw Haskell term. And this one says, okay, at the root, we have a we have this term. That's what's at the bottom, and it right arrows to 13. So this is what's on the bottom of the proof. And then we know that from looking at the rule for A plus, there has to be one derivation above it and then a second derivation. And this one here is one derivation, and this one here is a second derivation. So if you go and you look at B expressions, what does the rule for equals for B expressions look like? It looks something like, okay, A1 equals A2, where this is really the constructor equals, right? Somebody say, uh-huh. So the rule would look something like this, yeah, good, thank you. And it goes to I forget how, actually, I should probably look at it in the book to see, or is this the one you have to make up? No, you have to make up the, okay. So there's two rules for equals, yeah. And it goes to TT, if A1 arrow V1. Now, maybe this should have like a little A scrub, because this is the big step semantics for Booleans, and this is the big step semantics for A expressions. I don't know, maybe this looks better. But the A should cue you in, and the fact that this is a B expression should cue you in there. So I'm just going to leave them all for now. And then this one's true. When the side condition is that V1 equals V2. And there's another rule that says it evaluates to false if these two are not equal. So what does a derivation of an equals look like? So we want something called the, I guess to be, I need to look down here to be, okay. So if I wanted to start making this, I would change A expression to B expression. But don't go any farther. And now I got to replace these by the proper rule name. So I've got equals, greater than, not. Was it GT? I don't know. Greater than. This one's a not. And then there's a paren one. Is that all of them? I think there's only. Oh, and there's an and. Well. There's an and also. In fact, and that's a binary one. So let's leave it like this. So that's a and. So this is B and R, and this is a B not rule, and this is a B paren rule. And of course, these evaluate not to int, but to bool. And so let me get rid of all these ugly comments down here that don't make any sense. Now, so now I have a type that sort of looks like almost the right thing, except that here, when I look at this rule, I've got an A expression derivation for the equals. And for the greater than also, right? This one is also takes two. Now not takes a single B expression derivation. And takes two, and that takes a single one. So there's the data type for this thing, for these B expression derivations. Okay? But now I did half your homework for you. Ah! I guess I can put that file out there. It's a little bit tricky though. I mean, the thing is that like this this function here, this not prove, but the big step A prime, that's pretty straightforward. You can see what that's doing is it's just evaluating the expression plus A1, A2. So your big step evaluator is pretty easy, but the idea of building this derivation tree is less familiar. This is a kind of a tree structure, which is a derivation. And we're going to talk about them more today. Okay? Any questions?
I have a question.
Okay.
For
yeah, okay. I lost my B expression derivation though. I was stuck on the A expression. Okay, for what?
In the original B expression definition, I'm having trouble understanding the paren because it's B expression paren B expression. Is there supposed to be two B expressions there, or is that just defining paren as different from the A expression paren?
No, the A expression paren also just has a single A expression. It's just you take an A expression and you put parentheses around it.
Okay. Oh, I see it now.
Right. I mean, there's not two. If you're just putting parentheses around an A expression, there's not two A expressions in there. If we added something like pairs of A expressions, then you might have more than you'd have two. But Okay.
Got it.
I have a question.
Okay.
So when we do the conclusion, yeah, the function projects the conclusion of the type. I'm having trouble with the doing the part for equals because it's taking the A expression. So my question, I guess, would be when you're writing the conclusion for the big step B, how would it work for equals because it's using a different type than the
The conclusion
big step?
just looks at these things, right? And does it give back the pair, or does it just, oh yeah, this is a pair, really. It's an A expression paired with an int. And so then here, the conclusion would be a B expression paired with a bool. So here's the thing that's confusing people is that what I'd kind of really like to do here, but I can't, but Haskell's in this kind of we're using a basic form of Haskell. There are extensions to the language that would allow us to write richer types. But what we'd really like to do here is not to say, okay, B equals takes a B expression. It actually takes an equals with two A expressions. Right? This is a B expression, but we can't at this level specify which B expression. So we just have to say B expression. Whoops. So we got to just say B expression. Now, like if you look in the same thing, you have the same thing sort of in, yeah, you have the same thing here with plus, for example. Like this is got two A expression derivations above it. I mean, so improve is where it's interesting. And I think actually, oh yeah, the value of, yeah, concal isn't really that interesting of a function. I mean, if you're writing more things to put proofs together, it is a useful function. I think the only place we're using it here is to say, what it takes an A expression derivation and it returns the integer value that gets derived from that. So down here in prove, this is where we have to get specific and we say, oh, okay, it's an A plus R rule. Oh, and not only that, the argument has to be a plus operator. And so when you write the same, and so here in prove, you get specific where you're building the proof structure and you're examining the structure of an input. So your input looks like a plus. You go like, okay, if I'm going to be able to make a derivation of A1 plus A2 to anything, I'm going to have to use the A plus, the rule for plus in arithmetic expressions. I don't know. Did that help?
Yeah, that made sense. Thank you.
I mean, don't get fooled by the fact that this simply says B expression. It can't be, when you actually build one of these derivations, it can't be just any old B expression. It has to be an equals.
Yeah, that makes sense. Thank you.
Okay, any other questions? All right, well, I guess in a way, maybe the only fair thing to do is to replace the BIMS file with one that has this in it as well. But I probably ought to put it down at the bottom or something. I don't know. I'll think about it later, trying to restructure it so it's a little cleaner looking. No other come on, somebody must have a question. Okay. So, I mean, the point is we're building a data structure to represent a derivation. And so we'll talk about that more.
Wait, I have one more question. How many test examples do you want us to include?
Think of it, you know, like people often ask this kind of thing, and it's like, oh, okay, if I tell you 2, would you think that's enough? 1 is
Probably not.
Yeah. So somehow or other, I mean, you know, I don't mean to sound like an old curmudgeon, but I kind of a little bit can because I am old. You should think of this doing homework at the university level, at the upper division level, like you're doing your job, as if you had a real job and this was your job. And your boss said, okay, go implement this thing for me. I need these B expression derivations and I want you to go implement them and then run some tests to, you know, so that we can see that they're correct. Well, it's kind of up to you. You're not going to go back to your boss, I hope, and say, do I need to do 5 tests or 7? You know, it's just probably not what they're looking for in employees. They're looking for people that can, like, think about the thing and say, the problem I'm trying to solve here is to show that my code works. How can I do it? Okay, look, certainly if you're going to want to try one, you know, some that include basically all the different kinds of B expressions and look at the derivations of them. And then maybe you want to try some big ones and some small ones. I don't know. You might like to make sure perhaps that on the equal and the greater than that, you know, the subtrees on those are A expression derivations. Like, I don't know, do you want to say try one for each case, like, or all combinations? Now, if you could think of a good property and you were in 3015 last semester, you might be able to make a quick check, some quick check tests. But I don't really want to go into how to do that this semester. Okay? I hope that didn't, like, sting that I say that.
No, you're fine.
Okay, okay. Because, I mean, I don't know. I'm like,
Another
I don't want to,
question.
like, hurt anyone's feelings or anything, but okay.
No, you're good.
All right, good. So let's see. All right, I guess I want to go on. Now, last time, you know, it's kind of, I don't know, I guess things like that happen. I don't know. I kind of fumbled in the end, and I thought I edited the recording so that people that weren't here might not have realized that I thought I was wrong about something that I wasn't wrong about. And so I should just never think that. So it kind of got garbled at the end of the lecture last time. But let's look, so let's start over again talking about the small step semantics, because we didn't actually get that far into it. And so we're looking at, and the difference is the small step semantics, you're kind of like modeling each step of computation that, like if, you know, if I write down, I don't know, 2 plus 3 times 7, I got to do an addition. I got to do 2 plus 3, and then I got to take the result of 5, and then I got to multiply it by 7. So small step semantics is keeping track of kind of like all the operations that you have to do. Now, you know, you could disagree and say like, okay, maybe one of the operations that we don't care about that much is that one that turns a numeral into an integer. It depends on sort of like what you're trying to model, whether or not that should really be counted as a step of computation or not. Like if you're already dealing with stuff that's loaded into your computer memory, then it's already out there as a digit. If you're loading it from disk, then you've got to translate it into, you know, a binary int or whatever. So we could change the rule, but anyway, remember the transition system, and it's kind of cool, I think, that this form of definition works for describing all these different semantic things, you know, different semantics for different languages. So for example, our configurations gamma are A expressions unioned together with ints. Now, it's going to turn out that we're never going to have a rule that says, oh, and you can turn an int. Here's what you do with an int. Like if we look at the rules over here, there's no rule that just has a V goes to a V. This one might look like a V goes to V, but this is the one where we've got parentheses, but there's no rules where the left-hand side is simply a V. We've either got a V plus V and so forth. So we don't ever actually key off of this. The rules are defined by the structure, the syntactic structure of A expressions. And then, you know, I don't know, this last semester I got confused on this, and this semester I find it confusing. But when he goes to the small step semantics, he uses what I think of as a big arrow instead of the single arrow is the big step semantics. So anyway, this is a relation. It's a subset of A expression cross A expression unioned with A expression cross int. Which that is a subset of gamma cross gamma, because A expression is part of gamma and A expression. So here's a Cartesian product. So those are sets of pairs that consist of a first element that's an A expression and a second element that's a expression. And then these are ones where A expressions go to ints. And so these are all of the right formed. They're configurations paired with configurations. And then that's not really a minus sign. The terminal states are just the ints. And so now what he did here was he cheated just a little bit. He added integers into the syntax. But like I said, there's going to be no rule that goes off just an integer. So we have numerals, we have A1, op, A2, and oh, I didn't write down here. I mean, we had just done it last time. The ops are plus, times, and minus. And we can take an A expression and put it parentheses. And now we have a new thing, which is you can also have an A expression, which is just an int. So now all of a sudden, in a way, I don't know, maybe he only needed to say it was A expressions up here, not A expression union in, because he added ins to the syntax of A expressions. But like I say, there'll be no rules where the left-hand side is just a value. V oftentimes in semantic contexts stands for value. It just allows us to record sort of like parts of the overall A expression where we actually have reached a value, but we're not done yet. So like I said last time, there's three rules now for each operator. So for like plus, for example, you could say, okay, I'm going to go over in the left subterm of this plus term, A1, and I'm going to do some computation there. And then the small step semantic says, okay, if A1 goes to A1 prime, then A1 plus A2 goes to A1 prime plus A2. And in this one, I choose, okay, I'm going to do something in the right subterm. And so you end up with A1 plus A2 goes in the big step semantics to A1 plus A prime 2 or A2 prime. And that's because A2 goes to A2 prime. And the only time you ever actually eliminate like a plus sign by, in doing the semantics is when you've already computed the left subterm is to a value and the right subterm to a value. So maybe I don't know. Let me see. I wish I could see. What I can't seem to do is go to the whiteboard without stopping my share and then restarting it. All right, well, who cares? Okay, let's see if I can. I don't know. My pads work. Where's my pen? Oh, come on. What did I do with my Wacom pen? This is going to make me crazy. Hang on. I don't believe it's down this far. It fell off my desk. Okay, so let's see. Is it going to work even? Settings. Whoops, let's see. Stop share. I apologize. Let's see. Okay. Settings. Oh, maybe I need to turn it on first. There it is. Oh, I could set up the button. Okay. I'm not going to do that right now. All right, now let me go back and try to show you. So first of all, let me refresh your mind. Look at the rules. So these are the rules, right, for plus. And here's the rule for numerals. And so now let me try to go back and go to the whiteboard. And so, we could have something like, okay, num. Oh, right. He just draws underlines under them. So like, whatever. 7 plus 2, big step, I'm sorry, small step goes to 7 plus 2. Now, why is that? Well, why is this in here? This is in here because I can take this left one and it goes to 7. So this is my A1 and this is my A2 and this is my A1 prime and this is my A2. And so 7 goes to 7. And so now we've got, this derivation here justifies that this pair, 7 plus 2, comma, 7 plus 2, is in the big step semantics for, I'm sorry, the small step semantics. Every time I write that big arrow, I say big step, the small step semantics for arithmetic. But now, from here, I have to do another derivation to get kind of to the end, or almost to the end. And so then I get to 7 plus 2 because applying the rule that says, look at this one, and 2 goes to 2. So now I know this pair is in the relation. And then finally, only now does the rule that says 7 plus 2 evaluates to 9 hold. And that was the rule that's stated in there that says V1 plus V2 evaluates to V, if is super important, this concept of taking K steps in a small step semantic. Or if you add the star there, what you're taking is 0 or more steps following this relation along. So if this is a transition system, the K-step transitive closure of arrow is written like this, arrow sub K, and it's defined as follows. Gamma goes in 0 steps to itself. Okay, so that makes sense. And gamma goes in K plus 1 steps to gamma prime if there's some state gamma double prime such that gamma goes in 1 step, or, using the base relation, to gamma double prime, and gamma double prime goes in K, which is 1 fewer steps, to gamma prime. And so this is the K-step closure, transitive closure. And then the reflexive transitive closure of arrow is that arrow star is defined. So gamma arrow star goes to gamma prime if and only if there's some K such that gamma goes in K steps to gamma prime. And since K is a natural number and 0 is in here, we know that this could be gamma itself if K was 0, or it would be something that is defined in the transition relation arrow here directly, or it would be some more than 0 steps is defined here. 1 step is given by this, and K plus 1 steps is given, by this definition. So here's one example of a kind of a derivation using these small steps semantics. And I guess the point is that you can't what you're doing in each step is you're either eliminating a numeral, or in the case that you get to a value times, well, you can't even do it yet. You got to wait until you get value times value, then you can eliminate it. So but we did, here, so let's just go. This is only one of many possible sequences that would get you from 5 plus 1 times 8 minus 9 gives you the result of minus 6. So first we'd say, oh, eliminate the numeral 5. And I think we did that one here, right? This one goes to that. Okay. And then, okay, now we could choose whatever to do. Let's get rid of the numeral 1, but we could get rid of the numeral 8, or we could get rid of the numeral 9. So we're going, we did the 1. And then we know that there's a rule here that says that if I have a value plus a value, I can replace it by the v that I get by adding those two together. So down here, I have 5 plus 1. That's value plus value. So I can replace that by the actual value 6. So what did I do here? I got rid of not a numeral, but I got rid of a plus sign. So at each step, you're either getting rid of numerals, or once enough numerals are gone, you can start getting rid of operators. And so now I have 6 times 8 minus 9, and I got rid of the parentheses around the 6. And then I got rid of the numeral, turned the numeral 8 into an integer 8. And then I turned the numeral 9 into an integer 9. And then I did the subtraction operator to get 6 times minus 1 in parentheses. And then I eliminated the parentheses and did the minus. But there's lots of different paths. Any questions? No questions. All right. So this is, from the book section. I should have put a 3.5 there. This is from section 3.5. Now, at this point, he's not going to prove these things because we're still in the simple little tiny system. But I mean, you could try it on your own to prove some of the theorems that we claim here. He's going to wait until chapter 5 to show us how to do induction on derivation trees to prove things. But so if we have a big step semantics, on the big step semantics, we really want this property of determinacy. Like, we don't want to have a semantics where we say run the program A and you get the answer V1, and then at a different time you run the program A and you get a different answer V2. And so determinacy says, look, if you run A and you get V1, and then you run A and you get V2, then V1 better be equal to V2. So in other words, this arrow, the evaluation defined by this arrow relation is deterministic. It only gives you one answer. So now to prove this, what we'd like to prove is that this arrow relation is deterministic, that the big step transition relation arrow is deterministic. And prove it, we'd have to show it's true for all the axioms, because what's the way that we know that some A expression goes to some value? is that there's a derivation of that fact using the semantic rules. And so I can only claim A arrow V1 if I can find a derivation using the big step rules. And so here's the rules. We have like a rule for plus, and these are going back now to the big step rules, not the small step rules we were just talking about. So we have one for plus, minus, multiply, a parentheses rule, and a numeral rule. And so his theorem 3.13 is that this arrow, big step transition relation arrow is deterministic. And so how would you write this down logically? You'd say like, okay, if A goes, if A goes to V1 and A goes to V2, that implies that V1 is equal to V2. And we'll do the proof later, but it's by induction on the transition A, that should be an arrow. And so you have to look at proof by induction on the structure of the derivation relation that this is true and this is true. So, but you might also think about this idea that, back when we were defining functions, we had this property. We said, okay, f is a function if, or at least it's a partial function if it's a subset of A cross B and it's functional. In other words, for every X in A, and for every Y and Z in B, if f of x is equal to y and f of x is equal to z, then it must be the case that y is equal to z. So, I mean, this looks very much like this. And in fact, it really is. If we take this definition and you replace f by the arrow notation, and instead of using the infix relational notation, instead of writing f of x equals y, we would write x f y, or here with the arrow notation, if we have three configurations, we say gamma goes to gamma 1 and gamma goes to gamma 2 by the big step translation relation. That implies gamma 1 equals gamma 2. So proving that arrow is deterministic is equivalent to proving that this is defines a partial function. But remember that for big step semantics, we're taking the program and evaluating it completely until it's an integer. So I guess let me go down here because I have this remark here that's pretty good to think about, is that if I'm using big step semantics to show that gamma goes to some gamma prime, then there's like one big derivation that eliminates all the program part of this and returns it into just a number. But if I am using small step semantics, I have one derivation that gamma goes to gamma sub 1. Okay, there's one little derivation. That one maybe just eliminates some numeral. And then this one goes to that. Okay, maybe that eliminates another numeral. Maybe the next one eliminates an operator inside parentheses or something. And finally, you get to your gamma prime. Now, what this is sort of suggesting is that, like, okay, so then we could say, okay, gamma, the, arrow star to gamma prime. If you have this goes to that and there's a derivation, and then you have this goes to this and there's a derivation like that. So the choice of variables here is kind of suggestive because it's sort of saying like, I've got the gamma and I got a big step to gamma prime, and down here I've got gamma and I've got, after some number of small steps, goes to gamma prime. And that is kind of the next discussion, is that small step semantics is not deterministic. Well, because look here, I mean, for any operator, plus, times, minus, if I have A1 plus A2, let's say, I can choose the left subterm of the plus expression and go, oh, I'm sorry, that should be an arrow there, like it is down here. That should be an arrow to A1 prime. And evaluate in A1 to A1 prime, and then this whole thing evaluates to this. Or I could choose the completely opposite side of the tree structure and evaluate something over there. So that's why in the last little set of notes, we had 4 different places that you could evaluate, that one expression, I forget, whatever it was, 2 times 3 or whatever, times 8 minus 9. So we end up with lots of different results that you can't get with the big step. The big step only goes one place. So clearly, just by looking at the rules, the small step semantics is not deterministic. Here's an example. The numeral 7 plus the numeral 2 goes to the integer 7 plus the numeral 2, or it also evaluates to the numeral 7 plus the integer 2. So we have a situation where A can go to A1 and A can go to A2, and A1 is not equal to A2. So we don't have determinism. But, and this is a big but, we can show this nice thing that says that the reflexive transitive closure arrow star is deterministic if we go all the way down to a single value. So if I take an A expression and I evaluate as much as I possibly can using the small step rules, and then I take A and I evaluate again as much as I possibly can, and it's clear that there's different choices here. Their theorem 3.15 says, but we still always get the same answer. So that's a really nice relationship between, or way to think about the small step rules are deterministic. Now, if I added a rule, let me go share my screen in a different way. Let me share with this. If I added a rule that said something like, or if I just said V small step evaluates to V, this would cause huge problems, because now I would have the possibility of infinitely long derivations. Suppose that I had like 7 plus 2, and on my first one I got rid of the 2 as a numeral. Now I can go and do this one again, 7 plus 2, and I could go on like that forever. So, but when he writes, okay, what about when, so forget about this. This is bad. Let's see, can I make it red? Bad. Can't have something like that. We can't have any rule that allows us to kind of have a circle. And so, but if I say 7 plus 2, there's 2 ways to do this. I could go 7 plus 2, or I could go 7 plus the numeral 2 in one step. And then notice these come back together. Both of them, the only evaluation for either of them is to get rid of the numeral that's not eliminated. So it comes back to this. So the evaluation can diverge like this or like this, but then it comes back. And then after that, there's only one rule to apply, and I get the answer 9. So when he writes, you know, there's something very specific and that I think is kind of hidden, is that when he writes, okay, you know, well, let me just write it, the determinism for the small step semantics says, you know, A goes in 0 or more steps to V1. That's a single value. It's a value. And you've got and A evaluates in 0 or more steps to a single value. It's crucial that this is a value. That implies that V1 equals V2. Because this essentially means once you're here, once you have a single value, there's no more evaluation that can take place. And so he's not saying, you know, look, you can have, like if we look at the previous page, I mean, we had that, you know, 7 plus 2 evaluates to 7 plus 2. And so that's true. But see, this is not a value. This is an A expression with a plus in it. So this is not a V like this. This is an A expression. So even though this isn't the star relation, this is saying something quite specific. And if I go back and I look at it here, this evaluates to 9. And that is a single value, and there's nothing I can do from there. And even though this evaluated to that, and this evaluates to itself, it evaluates to that, it evaluates to that, it evaluates to that, it evaluates to this, from here to here. So, I mean, all those possible pairs are in the arrow star relation, but there's only one final value. And that's a really nice property to have for the semantics. We want that to be the case. Now, one of the reasons that small step semantics is useful is for looking at analyzing non-deterministic programs, because you can write non-deterministic programs, or let's say threaded programs or concurrent programs that do give back different answers, and you'd like to have a semantics that lets you examine that and see where is it that they're getting, why, at what point to analyze why is there possibility of getting different answers from the same program when I run it in parallel. So any questions? Okay, I think I made it on time today.